Hi guys, welcome to tutorial 6, acid and bases, right? So the first questions. Now the acidic nature of carbonic acid can be explained by both Arrhenius and Bronsted-Lowry theories. Using relevant equations, explain how carbonic acid can be classified as an acid according to both these theories. So write an equation for the following substances behaving as an Arrhenius base in water. Now what is Arrhenius base again? Arrhenius base is a compound that dissolves in water, producing high concentration of OH minus, right? So you just need to write an equations showing that how the following compound dissolve in water and producing hydroxide ions. It's actually quite simple here. Now let's say the first one, LiOH solid, right? So you plus with water. I don't put the water in so that I don't have to balance it in the first place. Second is because H2O is actually a solvent for the whole thing, right? It's just for the dissociation. So at the end, when you add water, you get Li plus, which is aqueous, and OH minus, aqueous. So as long as you show the formations of OH minus hydroxide ions, that will be good. Okay. So next, barium hydroxide, the same thing, guys. Try to dissolve in water, and then I will get barium 2 plus aqueous plus OH minus aqueous. Balance equation 2OH. Now, this is important where you have to write aqueous. It shows that the solid has been dissolved in water, changed into aqueous solutions. Okay, so in this case, the aqueous is a must. So that shows Arrhenius base. What about Arrhenius acid in water? Same thing. H3PO4 pure liquid. I'm going to dissolve it in water so that they can dissociate into ions. So it dissociates into H plus and PO4 3 minus, right? And balance equation, I have 3 plus, 3H plus. Same goes to this nitric acid. I dissolve in water. So for them to dissociate, so you get H plus and NO3 minus. Now bear in mind, an acid or a base without water, okay, under Arrhenius theory, without water, all these so-called acid-base solution, for example, solid, right, liquid, all these are non-acidic at all. Without water, they can't dissociate. When there is no dissociation, you don't see H plus and OH minus. So even though you put a dry litmus paper into this nitric acid liquid, you put a litmus paper in, dry, you put it in, you don't see any color change. By right, it's a turn rate, but it will not change the color due to no water or due to no H plus present. Because no water, there's no dissociations. All right, so that's question number 1. Very simple. Question number 2 is about Bronsted-Lowry acid and base, right? So write the equation to show that they behave as an Bronsted-Lowry acid. What is Bronsted-Lowry acid again, guys? It's a proton donor. Okay, so it must shows that the compound given here must able to donate a proton in water. So this one I can put it in so that you can see which one is donating proton, which one is accepting proton, right? So H2PO4 plus H2O, you want it to be an acid here. So what to do? It donates a proton. So H2 become HPO4. One at a time, guys. Okay, one at a time. So one proton donate to H2O, you get H3O plus. Simple. Again, this one, H2S, to act as an acid, you must able to donate the protons to the base here, which is the proton acceptor. So one at a time, HS minus. Okay, no more gas, is aqueous. Sorry, I forgot. Aqueous, 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 and plus with H3O plus aqueous. Again, guys, reminder, H3O plus also the same as H plus, so it's the same thing. All right, so from here, other than just write the equation, can I ask further questions on this? Now I have an acid here. Why? Because it donates a proton. At the end, I'm losing a proton here. See that? So I donate a proton, so this is an acid. H2O turn into H3O. This is a proton acceptor, so this is a base, right? And what about this? Let me change the color. Oops. Why is this things overlapping the Oops. Sorry. Let's continue from here. Okay. Okay, now acid and base, right? So what we call these as? So from an acid, after it donated the proton out, so this is what we call a conjugate base. Always remember, an acid will turn into a base after donated a proton. So what about this then? A H3O plus. Initially it's a base from H2O, it turns into H3O. So this is a conjugate acid. Okay, so this is how it looks like when we name a conjugate pair. Okay, let's move on to the next. Why is this thing overlapping? I'm sorry, guys. Okay, now the next one, Bronsted-Lowry base in water. So ammonia gas, how they react with water to act as a base. To act as a base, it must be a proton acceptor. So in this case, ammonia plus water, you get NH4 positive, accepting a protons from water, and the water turn into OH minus. Same goes to this CH3COO minus plus water. Oops. Sorry. Alright, you plus it with water, and then what do you get? You get CH3 because it's a proton acceptor to act as a base, CH3COO, H. Bring one hydrogen here, and remaining will be OH minus as well. So therefore, these two act as a Bronsted-Lowry base in water because they act as a proton acceptor. And did you see that? At the end, it's also produced OH minus. That also coincides with the theory stated by Arrhenius. Okay, so this is how it looks like. So this is the Bronsted-Lowry acid and Bronsted-Lowry base. Let's move on. Okay, let's continue. Write the formula for the conjugate acid of each of the following. So what is conjugate acid for each of the following? Conjugate acid formed from a base, right? From a base, it accepts a proton, turn into a conjugate acid. So what will be the formula for the conjugate acid for each of the following? Which means all this acting as a base by accepting a proton, then it turns into a conjugate acid. So very simple. What would be the formula for a conjugate base for this compound? This one will accept a proton, changing into H2CO3. H2O accepting a proton, you get H3O plus. Now, see that initially this one is negative, and when I add H plus, you get neutral. Here, initially is neutral. When I add H plus, you get plus. So by adding H plus, or when you are adding H plus into a compound, it will get a positive charge in extra. Alright, for example, this initially started with negative. So when you add a H plus, because it's a proton acceptor, what do you get? You get H2O. Or OH2 lah, it's the same, right? And what about this neutral? I add a H plus. From neutral, it turned into NH4, positive. So don't forget, if started with neutral, it will turn into positive charge ions. If started from negative, it turns into neutral. Okay, now all this shows that A, B, C, D all accepted a proton, turn into a conjugate acid. So these will be all the conjugate acid. Alright, next, moving on. Write the formula for the conjugate base of each of the following. So now, again, they want conjugate base for each of the following. Means conjugate base is formed from an acid. Alright, so an acid will donate the proton and turn into a conjugate base. So you need to take out one hydrogen from it. Take out a hydrogen plus from each of this, you will get the formula for conjugate base. So take out a hydrogen, you get H2 negative. See that? It's opposite from just now. When I'm taking out hydrogen, it turns from neutral into negative because you're removing positive from it. All right, same goes to this, it's neutral. And then when I take out the hydrogen, it turns into CH3COO negative. The H must be from here, not from the CH3. All right, from the OH. This is the acidic proton. And what about this? Take out hydrogen. Sorry guys, this is positive. Okay, so take out hydrogen from here, from positive become NH3, neutral. And this H2O3 minus, you take out hydrogen from it, you get CO3. Instead of minus, you get 2 minus, because you further taking out hydrogen plus from it, you get a more negative. All right, so yeah, that's it. Next, number 5, hydrogen bromide is a stronger acid than hydrogen sulfide. Identify the following statements as true or false, giving reason for your answer. Let's look at A. Okay, now the equilibrium constant for the hydrolysis reactions of HBr will be larger than H2S. Okay, now what does it mean by this? Look at the questions again. It says that hydrogen bromide is a stronger acid than hydrogen sulfide. If that's the case, can I say hydrogen bromide has more dissociation compared to hydrogen sulfide? Okay, let's write the equations out. HBr, okay, it's a stronger acid, right? So when they dissolve in water, you're actually getting H plus and Br minus. Okay, and here they say equilibrium constant for the hydrolysis. Hydrolysis means you add water, you're trying to dissolve it, of HBr, reversible then, because it's in equilibrium. If it is a complete reaction, there shouldn't be any equilibrium constant, so which means this is a reversible reactions. Okay, HBr, add water, reversibly change into H plus and Br minus. Okay, and then you have a K value here, which is concentration of H plus, Br minus, okay, and HBr. That's it. This is the equilibrium expressions. And for hydrogen sulfide, then same thing, comparing equilibrium constant. So you will get H plus and HS minus. Just take one H at a time. So we don't take up two H one shot. So we consider it one by one. So this is also another K value where you have concentration of H plus, HS minus over concentration of H2S, right? And here it says HBr is a stronger acid than H2S, which means HBr will dissociate more compared to this. See, longer arrow, shorter arrow, just to show you this one dissociate more. When the dissociate more means the concentration of these two will be higher, right? And that's why the equilibrium constant will be larger compared to this. Less dissociation, concentration of these two will be lesser, not decrease, guys. It becomes lesser because compared to this, because less dissociation due to a weaker acid. So therefore the K value will be smaller in this case as compared with the K value for HBr. Make sense? So the equilibrium constants for the hydrolysis of reaction of HBr, which is this, it will be larger than H2S, and it's a stronger acid. Makes sense? So this is true. And the reason is, you just explained what I did just now. HBr is a stronger acid, alright? So it will dissociate more to H plus and Br minus, hence increasing the concentration of product, making a bigger K value. That's it. You just need to explain one side. You don't have to explain both. Alright? So you can repeat again by watching the video again. So for part B, let me erase that. Part B, a solution of HBr will always have more H3O plus presence in the solution than H2S. This one I can straight away tell you is a true. Why is it true? HBr is a stronger acid. Like I mentioned just now, it dissociates more, it produces more H plus. H plus is the same as H3O plus, and HBr has always more H3O plus in the solution. It is true. Okay, so what would be your answer here? First, true, and then give a reason for your answer. HBr is a stronger acid, hence more dissociation into H plus Therefore, concentration of H2O plus is actually higher than H2S. Simple. All right, that's for B. Let's move on to C. Br minus aqueous is a stronger base than HS minus. That you have to be careful. Let me write the equilibrium again. HBr dissociates into H plus and Br minus, right? Now, from here, the HBr is actually an acid and it donates a proton, therefore it turns into Br minus. So what we call this as conjugate base. That's why they say Br minus is a base. See that? And H2S. I just simplify the reactions. H2O, H2O here. So what do you get? H plus and HS minus, right? So H2S supposed to be an acid, but a weaker acid than HBr. And what happened after they donate the H plus? Donated the H plus, it turned into conjugate base. Okay, so now I clarify. Br minus and HS minus both are actually base. Make sense? So now they are base now. And how do we know Br minus is a stronger base than HS2? To act as a stronger base, you must able to accept a proton because a base is a proton acceptor, right? Then we look at a backward reactions for both to know whether these Br minus or the H2S, which one is a stronger base, which one have the ease of accepting a proton. All right, now come back to the dissociation just now. HBr is a stronger acid, which means these reactions favor forward more than backward, longer, shorter. And this one favor backward more than forward. Make sense? Because H2S is a weak acid, less dissociation to the right. Based on the length of the arrow you can see. Alright? Now, since now we are looking at the backward reactions, for Br minus to act as a base, you must able to accept a proton and change it to HBr. And what happened to the arrow here? A shorter arrow compared to HS minus, which means HS minus is a stronger base because the ease of going backward to accept a proton is much higher for these reactions since they go backward more than forward. Make sense? So therefore here they say Br minus is a stronger base, so this statement is false. And why? Because H2S is a weak acid, hence for its conjugate base to go backward is easier. Okay, I repeat, H2S is a weak acid, hence for its conjugate base HS minus to go backward or to act as a base is better, is easier. Alright, so yeah, that's for C. Moving on to the next questions. Now, from here onwards, I guess all of it will be calculations. Alright, I'll get ready my calculator, so I'll do it on the spot and then work out the solutions. So number 6, calculate the concentration of H3O. Again, reminder, H3O plus same as H plus, guys, in each of the following reactions. So what is the concentration of this? So let's look at A. 0.0245 mole per dm cube. I try to standardize now since in the question they give per liter, so I just do it per liter. It's the same, in fact. Sorry. Okay, mole per liter then of HCl. So when it dissociates in water, now we know that HCl is a strong acid. Okay, HCl is a strong acid. So when deal with calculation, guys, in SEM 1 is all strong acid. Now you will get what? H plus and Cl minus, right? It dissociates. And the mole ratio is 1 to 1. 1 HCl, 1 H plus. So if you have 0.0245 of HCl, What is the concentration of H plus expect? Same, 0.0245 mole per liter. Make sense? Okay, then we can calculate pH. So no, we don't need to. They just want concentration. Yeah, that's the answer for A. That's simple, right? So that's A, and then move on to B. Let's continue. So what is the concentration of H3O plus in each of the following solutions? What about this? This one is not an acid, it's an OH minus, right? How do we do that? So let's write out the equations. LiOH turn into Li plus and OH minus, right? In water, of course. So initially the concentration is 0.37 mole per liter. Okay, and what is the concentration of OH minus expected? 0.37. Can I say that? Yes, because it's 1 to 1. 0.37, you get 0.37, and this is a strong base. Yeah, there you go. This is the concentration of OH, but that's not the answer because they want the concentration of H plus. So how to do that? Kw equals to concentration of H plus, concentration of OH minus. Do you remember that for pure water? And the Kw value at 25 degrees C, since it is not given, always assume that it's standard conditions. And here 1 times 10 to the power of negative 14 equals to concentration of H plus. And what is the concentration of OH now? Put it in. Because all of it are in water, right? So we can use this water constant to calculate. So we put in the 0.37, and then from here we can get the concentration of H plus. Let's do the calculations. Alright, divided by 0.37. Okay, concentration of H plus obtained will be 2.70 times 10 to the power of negative 14. So that is the concentration of H3O plus or H plus. Same thing in LiOH solutions. And you can see that the value, the concentration is so much smaller, right? And it makes sense because LiOH is an alkaline solution. The H plus is meant to be very low because the concentration of OH should be much higher than it. So yeah, so all makes sense, right? So let's continue for part C. A solution containing 0.0125 mole of calcium hydroxide dissolved in 250 ml of solutions. So here they don't directly give you the concentration. You have to find out the concentration of calcium hydroxide before you calculate the concentration of OH minus. Let's do it step by step. Number one, let's see what is the concentration here. 0. Oh my goodness. 0.0125 equals to mV over 1000, right? 0.0125 equals to m, unknown, V is 250 over 1000, and then you will get your m. Divided by 250, you get 0.05. So m equals to 0.05. This is mole per liter. Okay, this is mole per liter. So now we got a concentration of calcium hydroxide. The formula is, see that? Now this is not the answer because this is just the concentration of calcium hydroxide. And what is the concentration of hydroxide? Then we have to write the equations. Calcium hydroxide dissociate in water. You get calcium plus 2 hydroxide ions. See that? It's 2 here. That's the reason why we need to write the equations. So if this one is 0.05, what will be the concentration here? 0.05 times 2. Make sense? So I have 0.1 mole per liter here. So I got the concentration of hydroxide. Next, what to do? Next, we do the same thing. 1 times 10 to the power of negative 14, the Kw, concentration of H plus, concentration of OH minus. Okay, then you can straight away put it in. 14, H plus, and what is the OH minus? 0.1 here, total concentration of hydroxide. And then do the calculations. 1 times 10 to the power of negative 14 divided by 0.1. Get, yeah, why am I pressing the calculator? It's so easy. H plus is equals to 1 times 10 to the power of negative 13, right? So that's the concentration of H plus for C. Let me know if you're not clear, alright? So let's move on. Determine the hydronium ions and hydroxide ion concentrations in a solution of a pH 8.45. Wow. So you need to know what is the concentration of H plus, hydronium, same as H3O plus, and what is the concentration of hydroxide ion from a solution of pH 8.45. So what can we get from the pH value? We know that pH equals to negative log concentration of H plus. Am I right? Yeah. And now we have the pH 8.45 equals to negative log concentration of H plus. So from here, you make use of this formula, we can actually calculate the concentration of H plus. How do we do that? Anti-log it. Shift log negative 8.45. That's how you do it. Then you will get your concentration of H plus equals to 3.55 times 10 to the power of negative 9 mole per liter concentration, right? So that's the answer for H plus. Okay, so done with the H plus. And what is the concentration of OH minus? Use the KW because that composed of both H plus multiplied with OH minus, like what I did just now. 1 times 10 to the power negative 14. And then what is the H plus now? 3.55 times 10 to the power negative 9. That's 1. And unknown is OH minus. See that? And then from here, we calculated 1 times 10 to the power negative 14 divided by 3.5 times 10 to the power negative 9. Right? So you get your concentration of OH minus equivalent to 2.90 times 10 to the power of negative 24. Okay? Wait, it doesn't look right here. Let me calculate again for this one. Right? So let's go through that. This is the H plus, that's OH. Let's do this again. See? Sorry, my mistake. So the concentration of, that happened in exam, right? So the concentration of OH minus here is 2.82 times 10 to the power of negative 6. That makes sense. Because how did I notice that this is wrong? Because when I compare the concentration of OH and the H plus here, the concentration of OH should be much bigger than the H plus because this is an alkaline solution. Does it make sense? So this is how it looks like. Because this time I got negative 24, it's like wow. So it should be much higher than the H plus, then only you get an alkaline solution. So yeah, that's the answer. Okay, the concentration of both based on the formula. Okay, number 8. Calculate the pH of solutions having the following concentration of H3O plus. This is a bonus questions because they give you the concentration of H3O plus straight away. So then we just put into the calculation. pH equals to negative log what? 5.39 times 10 to the power of negative 3. There you go. And here same thing, pH equals to negative log base 10, guys. 1.43 times 10 to the power of negative 9. Then you will get the pH for yourself. Okay, so you calculate yourself on this because it's quite straightforward here. That's the pH of the solutions. And part B then. What is the hydronium ions or hydrogen ions concentration in solution with the following pH? Wow, right? So I will choose 2 to do it. Okay, I'll show you number 1 first then. Okay, number 1. So pH equals to 3.21, right? So 3.21 equals to negative log concentration of H plus from the formula. And then from here, you can actually calculate anti-log negative, don't forget the negative sign, 3.21. Anti-log negative 3.21, you straight away get the concentration of H plus equals to 6.17 times 10 to the power of negative 4. That's for part 1. Okay. For part 2, alright, 7.5, we do the same thing. Okay, 7.5 equals to negative log concentration of H plus. So what to do, guys? Anti-log negative, don't forget, 7.5, you will get the concentration of H plus equals to 3.16 times 10 to the power of negative 8. Alright, and the third one, which is the last one here, 12.43 is the pH, equals to negative log H plus. Don't confuse, guys, I know this is a basic pH, 12.4, it should be a base, but because they label it as pH, so the formula is still H plus here. Don't worry, okay? So then you do the same thing, shift log negative 12.43. You should get a very low concentration of H plus. In this case, because it's a basic, right? So it's 3.7 times 10 to the power of negative 13. You see that? Basic solution have very low H plus. Neutral solution, okay, not bad. And acidic solution, you have quite high. This is the highest concentration of H plus, which makes sense based on the pH. Alright, let's move on. Number 9. Calculate the pH of the solution form when 10 centimeter cubic of 1 molar has H2SO4 is added to 25 centimeter cubic of 1 molar NaOH. Now guys, this is different from the previous questions that we have discussed. This one, it does not give you the straightforward questions. This is a reaction between H2SO4 and NaOH. So before we actually calculate the pH of the solutions, we need to know whether these two compounds are fully reacted or any one of them are actually in excess before we identify the pH of the final solution. In fact, here they should write calculate the pH of the resulting solution. Right? When you mix them, they are neutralizing each other. This is an acid, this is a base. So after they have neutralized, what is the final pH? Okay, so let's find out. Let's continue. First, we write the balance equations. H2SO4 plus NaOH. Alright, you get Na2SO4 plus H2O. Balance equation, 2 water, 2 NaOH. Done. Then we calculate the separate mole. What is the mole of H2SO4 used here? 10 and 1 molar. So 1 times 10 divided by 1000, you get 0.01. That's the mole. Okay? And NaOH, do the same thing. 25 times 0 times 1 over 1000. 0.025. Right? So yeah. From here, as usual, what next? Limiting reagent and excess. Which one is limiting, which one is in excess? Let's check it out. We take the smaller one as usual. Let's do this again. Take it as a revision. So I have 0.01 mole of H2SO4. How many mole of NaOH required to completely react with it? So 1 to 2 ratio. 0.02 mole of NaOH needed, required. Are you okay? 0.02 mole of NaOH required, but how much do we have? 0.025. Right? So we have an extra of 0.005. 0.025, whatever we have, minus 0.02, which is what we require to react with all the, this is limiting then. Is that? Wait, sorry, no. 0.025, yeah, it is. This is limiting, this is in excess. Okay? So 0.025 minus 0.02, which is the one required to react, you will get the remaining of NaOH. 0.025 minus, you get 0.005. Of what? Of NaOH remain in the solutions. So the rest will be fully reacted. You get salt and water. So this part will be neutral, right? So we just look at the extra 0.05 mole of 0.005 moles of NaOH, which is extra in the solution, and from here we calculate the pH. Make sense? Okay, let's start with calculating pH. Now I have 0.005 moles of NaOH. All right, what is the number of mole of OH minus? Mole of OH minus equals to 0.005. Agree, guys? Because NaOH dissociate into Na plus and OH minus. Ratio is 1 to 1. If this is 0.005, here should be 0.005 as well. So there you go. You get the mole of OH, 0.005. Okay, to calculate the pH or POH, we need the concentration. So next, convert into concentration. 0.005 equals to mV. Now what is the V now, guys? You mix two solutions together. Of course, the total volume is 10 plus 25. So 35 over 1,000. And from here, 0.005 times 1,000 over 35, you get the concentration of OH minus. I just put it as this, equals to 0.143. Three significant figures, and that's mole per liter. So this is the concentration of OH minus that we have. All right, and next, what to do? Not N yet. You have to calculate the pH, right? But we don't have H. We can calculate POH first. Or you can use the KW to do that, up to you. POH equals to minus log concentration of OH, sorry. And then put it in, minus log 0.143. Okay, minus log 0.143. You will get your POH equals to 0.845. And how to get pH then? Because they want pH. So still remember, pH plus POH equals to 14. So pH equals to 14 minus 0.845. You will get sorry, my gosh, my bad, sorry. You will get 13.2. Okay, you will equivalent it to 13.2. Does it make sense? NaOH is the one in excess, which is an alkaline, which is a base. So the final pH of the solution is 13.2. So after the neutralization, you still have remaining moles of NaOH, and from the remaining moles of NaOH, you calculate the concentration of OH. After that, you get a pH of the solutions. All right, so that's how you solve question 9. Let's move on. Another similar type of questions, I'm going to show you again for this. Calculate the pH of the solution form, the resulting solutions, when 50 0.25 molar of nitric acid added to 50 0.1 barium hydroxide. Again, guys, we need to write the equations. HNO3 plus barium hydroxide. Balance the equations. You get barium nitrate plus 2H2O. I need 2 nitric acid. Alright, so done with the balancing. Next, calculate the mole. What is the mole of nitric acid used? 0.25 times 50. Divide by 1000, you get 0.0125 moles. Guys, you know what I'm doing, right? MB over 1000. get that? So I just don't show it. So barium hydroxide is 0.1 multiplied with 50 divided by 1000. You get 0.005. Alright, so done with the mole. Next, what to do? Limiting reagent, right? So let's check the limiting reagent. Which one is limiting, which one is in excess after they react. So, okay, let's erase this. It's distracting here. I don't want to confuse you. Okay, take the smaller one, which is this. I'm going to check this. If I have 0.005 moles of barium hydroxide, how many mole of nitric acid needed? 1, 2, 2. So you times 2, right? You times 2. Then you get 0.01. So 0.01 is the number of mole of nitric acid required. And how much do we have? 0.0125. Wow. So we have excess. So this is in excess. This is the limiting. So we only focus on the excess because the excess of acid or base will make a change to the pH at the end of the reactions. Am I right? Because at the end we know that you will get a salt and water, which will not have effects on the pH. So let's see. This is required and this is what we have. So 0.0125 minus 0.01, you get 0.0025 moles of nitric acid remain. Right? So after that, what to do? What is the number of mole of H plus? 0.0025 moles of H plus. Make sense? Right? Same mole. HNO3 dissociate into H plus and nitric acid. 1:1 ratio, guys. So it's the same. But this is not the end. Mole equals to MV or 1000 to get the concentration before we can calculate the pH. Therefore, 0.0025 times 1000 over the volume, guys. What is the volume? 50 plus 50, you get 100. So divide by 100. This is 100. Alright, this is 100. So then we get the M, which is the concentration of H plus, equals to 0.025 mole per liter. Now we got the concentration of H plus. Okay, which is this. Then what to do? pH equals to negative log 0.025. Then you will get a final pH minus log 0.025. 1.6. pH equals to 1.6. That's the answer for question 10. Okay. Moving on. Number 11. Calculate the pH change to 100 centimeter cubic of 0.2 molar HCl in a flask if 50 centimeter cubic of 0.1 mole per dm cube NaOH is added. Same thing, guys, but here they want the pH change. I'm going to show you that. Okay, let's change the color. Okay, initially write the equations. Of course, HCl, this is easier because it's 1:1. You're getting NaCl plus water balance. All right, ratio 1:1. Calculate the mole for each. I have 100 centimeter cubic of 2 molar. So initially I have let me show you in case 0.2 times 100 over 1000, I will get the mole of HCl used initially. Alright, so 0.2 times 1000 times 100 over 1000, you will get the answer of 0.02, so 0.02 mole here. Okay, and what is the number of mole of NaOH added into the flask? 0.1 times 50 over 1000, so you get 0.005 moles. Okay, now that's the moles. Again, which one is an excess, which one is limiting? Now, good thing is this is 1:1. See that? So I can take the smaller one and straight away say that is the limiting reagent if it is 1:1. So straight away this is limiting reagent because it's smaller. So this one is in excess, right? And how many moles of HCl do we need to react with NaOH? The 0.05. So if I have 0.005 moles of NaOH, how many more HCl needed? 0.005, of course. Right? Required to react. So then what to do? The difference. I want to find the remaining HCl solution. So 0.02 minus 0.005, you will get the remaining HCl. You get 0.015 moles of HCl. So we got the moles remaining. Next, we're going to calculate the concentrations, right? So what is the concentration? 0.015 equals to mV over 1000, right? So what is your m? This is what we are calculating. What is the total volume? 100 plus 50, you get 150. So I change that into 150, the volume. Then do the calculation, 0.015 times 1000 over 150. So the concentration of the H plus, okay, just straight away write this, for the acid is actually 0.1 mole per dm cube. Okay, up to here you get a concentration of H plus. And what is the pH at the final reaction? So we can straight calculate pH equals to negative log 0.1, and then you get your answer, negative log 0.1. Oh yeah, nice. pH equals to 1. That's the final pH, guys. Okay, this is the final pH. But they want the pH change. What is the initial pH then? We start from here. Initially, the HCl solution is like that. And what is the concentration? 0.2. So calculate the initial pH. pH equals to negative log 0.2. Makes sense? Because initially there's no NaOH added. It's just this. This is the original concentration. So then we can get the pH equals to negative log 0.2, 0.69. Okay, negative log 0.2. 0.6, 0.7. Initial pH is 0.7. That's initial. We use the initial concentration here. See that? Okay. Initial pH is 0.7. Final pH is 1. So what is the change here? 1 minus 0.7. The change is 0.3. So pH change is 0.3. Simple. Alright. So that's the answer. pH change is 0.3 for 11. Let's move on to 12. Now 25 ml of 0.05 m. Now this capital M is mole per dm cube, guys, is concentration. Don't confuse. Neutralize 40 ml of nitric acid. Determine the concentration of the acid. Wow. First, write the equation as usual. So HNO3 without knowing the concentration, unknown, but the volume is 40 ml. Okay, and add up with barium hydroxide. And what is the amount of hydroxide? 25 ml on 0.05 molar. This is the amount, and this is exactly the amount that you can neutralize all the acid here. Imagine you're doing a titration. This is unknown. Okay, and what do you get? Barium nitrate, of course, plus H2O, because it's neutralizations, and we're going to balance it 2HNO3 to water. Done. Okay, ratio is done, information is done. So how do we know the concentration of HNO3? First, calculate the number of mole of barium hydroxide used. 0.05 times 25. Okay, over 1000, you get 1.25 times 10 to the power negative 3. Alright, so this is the mole. And how many moles of nitric acid needed? If they said this is the amount that fully neutralize all the acid. So look at the ratio 1 to 2. Right? So this value you need to times 2 to get the mole of nitric acid, which is answer times 2. 2.5 times 10 to the power negative 3. This is the mole of acid, the nitric acid. Okay? Now, we got the mole of nitric acid. We have the volume of nitric acid. We can calculate the concentrations. So 2.5 times 10 to the power negative 3 equals to MV. V is 40. Because they said this amount neutralize 40 ml of nitric acid. So we need to know what is the concentration of nitric acid at 40 ml over 1000, and then same answer times 1000 divided by 40. So initial concentration of this nitric acid N is actually 0.0625 mole per dm cube. So that's the answer for question 12. Alright, let's move on. Okay, 13. A titration of a 25 ml sample of a hydrochloric acid solutions of unknown molarity reaches equivalence point. Still remember? Neutralization done. When 38.28 ml of NaOH has been added. So this is the amount of NaOH added to neutralize, to fully neutralize these ml of hydrochloric acid, and the concentration of hydrochloric acid is still unknown, like the case just now. Good thing is they give you the equation is 1 to 1, so let's do this. NaOH added is 0.437 times 38.28. What is the mole of NaOH used over 1000? MV or 1000 here, basically. 0.437 times 38.28. Alright, you get 16.7 over 1000. So you get 0.0167. This is the mole. Okay, and if that's the mole needed to neutralize all the acid, what is the mole of acid in it? Ratio is 1 to 1, so 0.0167 then of HCl. Now we got the mole, we got the volume. Okay, we do the same thing. MV 1000, 0.0167 equals to M. V is initially, before titration, is 25. We want to know the original concentrations. Divide by 1000. Alright, so times 1000 divided by 25. So the concentration of the acid initially, the hydrochloric acid, is 0.670 mole per liter, or mole per dm cube, same. So that's the concentration of the HCl originally before the NaOH added. Alright, that's 13. And we're done, guys. We have another 2 questions. As usual, I will leave it to you for the last 2 questions, and we will discuss it during our session so that everybody revise again on the last 2 questions, or maybe you can try it first, and then at the end during the tutorial sessions I will show you the answer. Alright, thank you for watching for this week tutorial, and summary videos already up, and this is the tutorial. Thank you.